Welcome to e-Pathshala lecture series in computer science. This is a course in cloud computing. We continue our discussion of virtualization in this module as well. So, the learning objectives of this class will be, we will look at the methods of virtualization, the specific methods of virtualization, how to implement CPU or hardware virtualization. We will look at one specific example of Zen, which uses which is a virtualization software, followed by summary. So, in the last class we looked at what is virtualizability. We saw that some hardware are not virtualizable easily. There are certain mechanisms or certain problems in that particular hardware by which we are not able to virtualize it. We looked at Popek-Goldberg theorem for that, and we saw that x86, which is the most popular architecture, I say, is not virtualizable, and we just briefly described the methods of virtualization. In this class we will look at the those methods, how to implement, and we will look at how Zen works. So, we saw that there are three techniques: emulation, trap and emulate, and binary translation. Let us look at little detail of how these work. So, in emulation, as the name suggests, the VMM will behave like a like the other expected guest OS. So, here we run our guest OS and the application in the user mode. We deprivilege our guest OS, we run the deprivileged guest OS in the higher ring in x86 specifically. Every time there is an instruction, the host or the VMM will trap to that, will translate it, will execute that specific instruction and then go back to the user mode. So, there will be a continuous context switching between the kernel mode and the user mode. The user mode, for every instruction in the user mode, the kernel mode will have to react to that. So, this is basically a method of interpretation. As it goes without saying, it is very expensive to do interpretation, because for every instruction there is a switch between the two virtualization. In virtualization, emulation is not required. When the ISAs are different, when we run two different ISAs, programs written for one ISA will be run in another ISA. There, every user instruction has to be trapped by the VMM and translated to the target ISA. So, that will be required, but in this case it is really not required. A simpler mechanism, because in a virtualization we do not expect a different ISA, we expect the different OS, different operating system. So, operating system targeted for a specific ISA will an application will run in that operating system, but this whole application and that operating system will be run on top of another operating system, but both will be targeted for the same ISA. So, we really do not need to do an emulation. A simpler mechanism is called trap and emulate, where the guest environment application and the guest OS again will be run in the user mode. The guest OS will be deprivileged, VMM will run in the privileged mode. The normal instructions of the user process in the user mode will run directly, just like a normal non-virtualized environment works. We will make it work in a similar manner. The user mode instructions will run in a directly on the hardware. It will not require the intervention of the VMM. Only the privileged instructions that will be run by the guest OS will be trapped to VMM, and the VMM has to take control of those instructions. So, trap and emulate, whenever VMM traps, it executes the necessary equivalent in the underlying ISA as is expected by the user and the guest OS. and then it returns control to the guest in the user mode. So, the VMM runs in privileged mode. Every time there is a privileged instruction that traps to the VMM and it works fine. User mode code runs at normal speed. In the user mode, all instructions are directly executed in the hardware and therefore, it runs in the normal speed. Therefore, from the non-virtualized environment there is no change, but kernel mode or the privileged code will be run at a slower speed because those have to be trapped and emulated. But what happens now when there are several such guests available? Each of these guests are trying to run privileged instructions and therefore, so many trap and emulate for each guest will definitely become more expensive. So, this is our trap and emulate mechanism, where we have the VMM running at the in the kernel mode and we have the user process and the guest OS running in the user mode. Normal user processes will execute only when the privileged instructions in the guest OS will be executed, that will trap, an emulation will be done and then the results will be returned to the user. So, what is a problem in this? There are certain ISAs like x86 which cannot be emulated. We will shortly look into that. This is followed by Popek-Goldberg theorem. Intel x86 is the example for it. Let us look at this example. x86 has a POPF instruction which basically can run in both user mode as well as the privilege mode. So, it essentially does this, it essentially loads the CPU flags from the stack. So, in privilege mode all flags will be replaced. In user mode only some flags are replaced, but when this specific instruction is run in the user mode, it does not generate a trap, it does not trap to the operating system. The next mechanism that we look at is a binary translation. In binary, the binary translation solves this problem. So, some privileged instructions run in both the modes, in privilege mode as well as in user mode. In user mode it behaves in a different way and in privilege mode it behaves in a different way, is that causes a lot of problems like we saw, and this problem is resolved by binary translation. In binary translation, what we do is the guest vCPU is run in the user mode as usual. If the guest vCPU is trying to run in the kernel mode, that time VMM checks every instruction and ensures that, inspects all the instructions and ensures that the sensitive instructions are trapped. So, translation happens, it is not emulation, all instructions are not translated, only the guest OS's sensitive instructions will be translated to something that will eventually trap to the VMM when it is run. So, VMM checks all the instructions, non-sensitive instructions are not done anything, only the sensitive instructions will be translated to an appropriate instruction according to the ISA. So, performance will be worse than trap and emulate because another layer of inspection is happening. All the normal instructions are going and executing, all the trappable instructions will be trapped by the VMM anyway. In addition to that, we have a set of sensitive instructions which are not privileged instructions by the ISA. We have to take care of this by the binary translation. So, therefore, the performance will definitely be worse, but there are certain optimizations that can be possible, which is by caching the already translated set of instructions. We translate a set of instructions and then store it in our cache, and later on we try and see whether it is already cached or not, then no need to retranslate the same set of instructions. If it comes back, we can use the cached translation. If it is not available, then we translate. So, this is our binary translation, where we have the VMM running in the kernel mode and the guest OS and the user process application running in the user mode. Here the VMM will check the instructions, read the instructions. If it is a special instruction which is not going to trap normally, it will be translated using the VMM, and then it will be returned. So, this is how a binary translation will work. Let us now look at what actually happens in a CPU virtualization. But before I go into CPU virtualization, let me just reiterate this, that HAL virtualization, hardware virtualization, machine level virtualization and CPU virtualization are all meant in a similar manner in our discussion. So, as we saw from our discussions, we can think of 4 different types of methods. One is emulation, where we saw interpretation. One is full virtualization using dynamic binary translation. We will see how we discussed, but we will see how binary dynamic translation works. And then we can have para virtualization, and finally, we can have hardware assisted virtualization. These are 4 practical methods of working with virtualization. So, we start with the first technique, which is emulation, so we interpret the guest code, and only those hardware components are emulated, though that is different from what is expected by the incoming process. Therefore, CPU and memory are sufficient to emulate. So, emulate the CPU, emulate the memory, and it can be done. However, as we already seen, performance will not be as good, and therefore, it is not a preferred method. In case it is required, some additional mechanisms can be implemented. Now, let us look at what exactly we are looking for. We want to run an existing operating system and application in an isolated virtual machine. So, we should be able to run many such isolated VMs, and there should be some entity which will supervise the whole process. So, what can go wrong in this scenario? What will make our environment of running isolated VMs along with their host operating system and the application on top of different operating system or a supervising operating system unsafe? Those instructions which will be executed by the processor that will try to modify the state of the machine, or it will behave differently in 2 different modes, as we saw in the POP-F example, or it will fail silently in a certain mode. So, those are the instructions that are unsafe. So, how do we ensure safety? We do by inspecting the code. We saw that in emulation we have to inspect all the code. Rather than inspecting all the code, in binary translation, as we saw, that method can be applied for a virtualization in practice, and we can only inspect the important instructions, rewrite the instructions which may cause a problem. So, what will happen to the performance? Of course, the performance in Popek-Goldberg, one of the properties of a VMM is that the performance of a virtualized environment should be near native. How do we obtain that use in a practical environment? We make sure that most of or the bulk of the instructions are executed in the native speed. We can do that by using what is known as full virtualization. Here we apply the method of binary translation and trap and emulate, and we call it a full virtualization. So, in full virtualization, the guest operating systems, multiple guest operating systems will share the resources, and hypervisor is not known to the guest operating system. So, the guest operating systems are unaware of the presence of the hypervisors. This since it translates only the privileged instructions, the hardware it is expected that the hardware should be a virtualizable hardware, since the guest OS is accessing the hardware, is aware of the hardware. So, the guest OS is running, and guest OS is expecting that it is running on top of the hardware without being aware of changing the privilege level. So, what happens when the hardware is not virtualizable? We cannot do a full virtualization, just our x86 architecture is not virtualizable. So, therefore, after the problems of Popek-Goldberg came into light, for a very long time x86 was thought of that cannot be virtualized. Only when the full virtualization came with a binary translation, then only we could understand that there is a possibility of virtualizing x86. So, in x86, if we want to virtualize, we need to run the guest OS in at a higher ring. We cannot run the guest OS in the lower ring because we have the VMM. So, we run the VMM in ring 0 and we run the guest OS either in ring 1 or in ring 3, along with the application, or in ring 1 above the privilege level, ring 0. Requirement that the guest OS should run at a higher ring without knowing, without telling the guest OS that we are running you at a higher ring creates many problems. Some of these are this instructions, some sensitive instructions. We saw that x86 not all instructions are not all critical instructions are privileged instructions. There are sensitive instructions which, like POPF, can run in both the modes, and they cause lot of problems in the user mode, in the privileged mode and user mode, but they do not trap when run in the user mode. Ring aliasing is the problem of running the OS at a different ring level. What happens is, since the operating system is expecting certain privileges when they are written in to be run in ring 0, easily the OS can find out that it is not running in the correct ring, and therefore, it does not behave properly. And the third problem is the address space. What happens to the address space that is assigned to the operating system? Now, that address space is to be shared by the virtual machine monitor or hypervisor as well as the guest OS. Therefore, guest OS does not get to access the complete address space as is expected. Again, when the guest OS is not expecting to be having to have less privilege than it is written for, there will be difficulties. So, how do we resolve the problem of critical instructions, sensitive instructions running in both the modes, etc., by doing a dynamic binary translation? So, we already saw what is a binary translation. I run the user mode code directly on the hardware. I trap only the I translate only the critical instructions in the kernel in the guest OS and make them trap to the VMM. That is a binary translation. These critical instructions will be converted to what is known as a privileged instruction. So, there is a set of sensitive instructions which will behave differently when they are running in user mode and kernel mode. When they are trying to run in the kernel mode, we translate them to a something that will be always necessarily that will trap to the VMM. This when we done it in a dynamic manner, the translation, the binary translation is done in a dynamic manner, which means that we cache the translated code, we take a basic block and we translate that block, and when the next basic block comes, we compare it with the already cached translated earlier blocks, and if already a similar block is available, we reuse them instead of translating everything. This is called a dynamic binary translation. So, we do a full virtualization using a dynamic binary translation. So, this is our dynamic BT full virtualization. So, this is our host hardware. The VMM runs in ring 0, guest OS runs in ring 1, ring 2 is empty, does not have anything, and ring 3 runs user applications. When the user executes an instruction, it can directly execute on the hardware without bothering about what is there in the in between layers. When it executes the sensitive instruction, it traps to the OS. The OS will in turn be translated by the VMM in a dynamic binary translation, and those codes will then be run on the host by the VMM. This way, a full virtualization using dynamic binary translation can be executed. So, what is the problem of this? There is a hardware emulation for all those critical instructions, therefore, that costs performance issue. There are certain cases where this binary translation does not work. If there is a self modifying code at runtime, the code is changed by the operating system. So, therefore, even if we do a translation, an advanced translation of the code, how the code is going to be modified is not known, therefore, nothing can be done. For self referencing code, the references will change, therefore, thereby causing a similar problem of not knowing from before what code is going to be executed, and for any real time system it is very difficult because of the time, because of the performance issue. What is the solution if all largely full virtualization with binary translation or dynamic binary translation works, but there are certain cases where it does not work, where we can use the next mechanism, which is the para virtualization. Here, rather than letting guest OS think that they are running at the highest privilege mode, what the suggestion came is that why do not we modify the guest OS little bit to make it aware of that there is a VMM. So, in this case the guest OS will be communicating. So, the guest OS is aware of that there is someone, I do not have the privileges. So, therefore, it will generate a call in turn which is which will trap to the VMM itself. Zen introduced this and largely and made it very popular. So, guest OS is modified and is run in either 1 or 3. Guest is fully aware of this. The privilege instructions, no need for a translation of that. It will use a hyper call, a special call to trap to the VMM. Then VMM will execute. Thus, VMM is responsible for handling the virtualization fully. So, here also the user applications will directly execute their code on the hardware. Here the guest OS will generate a hyper call and will will go to the virtualization layer, and virtualization layer will translate. Now, what are the problems here? The guest OS is modified. So, therefore, that causes a lot of problems in the guest OS. We need a tight coupling between the guest OS and the hypervisor, hence compatibility will become an issue, and every time there is a change in the hypervisor, all the guest operating systems have to be recompiled. Now, so many problems and difficulties in making changes in the operating system and the ISAs can be resolved by the manufacturer themselves. So, some instructions may be redefined, the ring can be readjusted, so that these problems of critical instruction not trapping as we faced in the full translation, full virtualization is not there. So, all these software changes, modern x86 architecture as Intel has come up with, meets the Pope-Goldberg requirement. This is VTX, Intel VTX, and AMD V are two hardware, two ISAs which meet the requirements. This VTX introduces the two modes, one is the VMX root mode and the other is the VMX non-root mode. The VMX root mode runs the VMM, non-root mode runs the guest operating system. Both of them supports all the 4 rings, and the guest need not be modified like Para virtualization, they can be run as it is, but they are running in non-root mode. Every time they run a privilege instruction, rather than directly accessing the hardware, they trap to the root mode and the VMM takes over the control. So, this is the non-root and this is the root. There is no, essentially looking at it, there is no difference, but every time the non-root tries to execute something, it traps to the root mode. So, what are the challenges? The guest OS is unmodified, so all legacy OSs can be allowed, but since the unmodified guest does not know about the virtualization, so the advantage of virtualization is not taken. This can be resolved by running a para virtualization also. So, this is the summary of CPU virtualization that we looked at emulation, we looked at the modern virtualization techniques, and we looked at the hardware assistance of Intel VTX approach. Let us look at Zen, which is a case study of para virtualization. This is the name is next generation, that is how the Zen has been coined. It is a virtualization system, uses para virtualization. These are the virtual machines, they are called domain or DOM. The DOM 0 is the main domain, and there are DOM U's which can run different types of guest OSs. So, hypervisor is the main component, and in DOM 0 there are domains DOM 0 and DOM U. In DOM 0 it is a modified Linux kernel, and this is the main virtual machine. This has special rights and can access the physical resources through the VMM. It interacts with all other virtual machines, and DOM U will be the all other virtualized operating systems that will be run, and there is a para virtualized VM which is the DOM U PV guests which can run Linux, Solaris, etc., and a full virtualized VM which is the DOM U 8 VM guest which can run unmodified operating systems like Windows. So, what is the Zen project has been very popular, and it has been taken over by many companies. Sun Microsystem, HP, Novell, Red Hat, they all have different ways of adapting Zen to their work, including IBM. So, we come to the end of this module and we come to the end of virtualization. We looked at in this module the different methods of virtualization, the 3 types, and then we saw how CPU virtualization is implemented using the 3 methods, and then we looked at how Zen works. Now that we come to the end of virtualization, we talk about the next mechanism or technique on which cloud depends, which is the web services. These are our references. Thank you.